This is lecture 19 of Physics 210A, that is thermal physics, and this lecture is going to be problem solving session. Number 7. We are going to solve 4 problems related to phase transitions and whatever we have learned about them in the previous lectures. Problem 1 is about an alternate derivation of Clausius-Clapeyron equation. The idea of doing this problem is that it shows you what dp dt means on the equilibrium line and how on this line a partial derivative becomes the full derivative. So for this, what you're being asked to do is use ds equals partial s partial t with respect to at constant pressure dt plus partial s partial v at constant temperature dV. This is going to be constant volume. And one of the Maxwell relations to get Clausius-Clapeyron equation. So let's look at the solution. If I look at the PT diagram of the phase diagram, and here is the phase equilibrium line, phase 1, phase 2, then I can go like we did earlier, either from for this problem, point say x to y, and on this dt is 0, and this is what I'll be using here, and in the previous lectures we have also gone across keeping p constant, but that I'll not be using here. So as we go across from x to y, I get ds is equal to dt term is 0 plus partial s partial v at constant temperature dV. And now we use the Maxwell relation that partial s partial v at constant temperature is equal to partial p partial t at constant volume. So I get, using this, that delta S as I go from x to y, and going from x to y is equal to partial p partial t at constant volume delta V x to y. X and y are very close, so I can actually write S y, which will be S1 minus S2 is equal to, now comes the point, dp dt at constant volume actually is the full derivative now. Why? Because I'm crossing the phase equilibrium line, and P is a function of T only on the equilibrium line. And then I can write here V1 minus V2. So this is a crucial point, that partial P partial T, keeping volume the same, is the same as the full derivative of P with respect to T at the equilibrium line, because there is no dependence on V. P depends only on T. And therefore, what we get is that delta S is equal to dP dt delta V, or dP dt equals delta S over delta V, both a specific entropy and a specific volume, and this is the desired equation. Problem 2. And this is taken from Finn's book. A small amount of pure liquid is contained in a glass tube from which air has been removed. Volume of the tube is much larger than the critical volume. Now, before I state the problem, let me show what's happening. So what we have is a glass tube. It has certain volume, and one has filled some liquid in it. Obviously, if air has been removed, this liquid will also give some vapor. And what do we mean by critical point? Recall from the earlier lectures, and I'm going to now make PV diagram because the problem also asks about that. When you have at a constant temperature the substance going through different phases, what you get is a liquid phase, then it goes into a liquid vapor phase, and then the vapor phase. A liquid phase, liquid vapor phase, and the vapor phase. And the topmost point here is the critical point. And here just an inflection takes place. And beyond this, it's all gas. Here it's all vapor. And here it's all liquid. I'm just showing it for liquid, vapor, and gas. Recall that the lower portion also has solid vapor, and if you go to really to the left, very small volume, you also get the solid phase. So the problem refers to this. And now the problem asks, describe what happens as the temperature is raised along path xy. I'm going to show that path on the PV projection of PVT diagram. And so what they're asking is that in this PV diagram, here is the critical point right here, and path xy is shown to be here. X, y, and in between there is z. And they're also asking what will happen if liquid volume is Vc and temperature is raised. So this problem is really makes your understanding of this whole phenomena quite clear, also makes you understand the graphs nicely. So let's now find the solution. So here is this PV diagram, and here is this dome through which this transition curves go, and this is how the temperature is increasing. These are constant temperature curves, and you are increasing temperature from x to y via z. So you can see that at x we have liquid plus vapor. That makes sense because in this glass tube, air had been removed, so there was this liquid and there was some gas. As you raise the temperature, as you approach Z, let's say we go to Z plus, then all liquid turns into vapor. And if you go further up, suppose you cross the critical point, so then you'll go into the gas phase. So beyond critical point, you'll be on a curve like this. Why? We will see. Blurry fluid, which is neither gas nor vapor, it's all just blurry fluid. Similarly, for the second part, again, I have this PV diagram, and now in the slope, I'm right at Vc. So here is liquid plus vapor, and as temperature is raised, liquid plus vapor is going to C point and turn into blurry fluid, call it gas or whatever, directly. In the difference between this and the earlier case is that in the earlier case, we went through a vapor phase. Now, the whole thing goes into the blurry fluid directly. That's the answer. Problem 3. This is also taken from Finn's book, Finn's Thermal Physics, and it says the equation for sublimation and vaporization vapor pressure are log P equals 0.04 minus 6 by T for sublimation and log P equals 0.03 minus 4 over T for vaporization, where P is in atmospheric units. A. Find the temperature and pressure of the triple point, comma. B. Find the latent heat of vaporization and sublimation. And C. Find the latent heat of fusion. So let me explain what all is being asked. If you make the P-T diagram, you have one curve here and one curve here. This is, on the left is solid, then you have liquid, and then you have vapor. Now the process from going to solid to vapor is sublimation. Process of going from liquid to vapor is vaporization. And where is the triple point? This big black dot, right where all the curves meet, is the triple point. So what is being asked is, what is the pressure and temperature at triple point? What is the latent heat for sublimation and liquid? Obviously, if you're going from solid to vapor, that latent heat is going to be more than liquid to vapor, because solid is more bound. And then we want to find the fusion latent heat, and fusion part is right here. Where solid goes into liquid. So these are the three problems that we're doing. So again, let me make this P-T diagram. Here is solid, here is vapor, and here is liquid, and here is the triple point. When you are given that log of P is equal to 0.04 minus 6 over T, and log of P is equal to 0.03 minus 4 over T. This is for sublimation, and this is for vaporization. You realize from the lectures that it is assumed that V, vapor, is much greater than V solid or V liquid. So in Clausius-Clapeyron equation, just V vapor comes in the denominator. Now at triple point, T and P are the same for solid and liquid side. What I mean is, if you look at this curve, here is this triple point. Whether I come on this curve, which is log P equals, not this curve. I'm going to erase this. Whether I come on this curve, which is log P equals 0.03 minus 4 over T, or whether I come on this curve, which is log P minus is equal to 0.04 minus 6 over T. The pressure is going to come out to be the same. And this implies at T, P, the triple point, I'm going to have 0.03 minus 4 over T is equal to 0.04 minus 6 over T. And this gives you 2 over T equals 0.01, or T triple point is equal to 200 K. That's one. Now we want to find the pressure. So pressure is also very easy. I can plug this number into any one of the equations. So pressure at triple point, P equals 0.03 minus 4 over T, or 0.04 minus 6 over T. Put T equals 200 K, and that immediately gives you P equals 1.01 atmosphere. This is log of. So that's quite easy. Third, we want to find the latent heat of fusion. Part C, we want to find the latent heat of fusion, and for this I'm going to do a trick, and you will see what I'm going to do. Now, as you come from solid to vapor around the triple point, you're going to come from, say, point 1 to point 2. As you go from vapor to liquid, you're going to go from, say, point 3 to point 4. And then, as you go back to solid to point 5, you're basically coming back to solid. And if you're very close to the triple point, here's the triple point. Then 1 and 5, all the properties are going to be the same. Now the latent heat, L, is nothing but T delta S. So latent heat of this is part B and C together. latent heat of sublimation is T triple point times S2 minus S1. Latent heat of vaporization is equal to T triple point, we are doing everything near triple point, times S3 minus S4. And latent heat of fusion is going to be Tp S4 minus S5. Now, part B had actually asked for the latent heat of sublimation and vaporization. I should have done that earlier. So, let me first finish part B. You're given that log P is equal to, for vaporization 0.03 minus 4 over T. If I take the derivative of both sides, I do d by dt, I get 1 over P dP dt equals 4 over T square, or dP dt equals 4 P over T square, and P over T is nothing but 1 over V by ideal gas equation. So, this is 4 over TV, because P V equals RT. So, there is going to be an R also. And by the equation that we had derived earlier, this is nothing but L over TV. So, L is known. This gives you L vaporization equals 4R. And by the same method, if you are given P or log P equals 0.06 minus 6 over T for sublimation, then L sublimation is 6R. So, we have found L sublimation and L vaporization, and as I said earlier, L, and this is near the triple point, because that's where we are writing these equations near that, we are assuming that. So, now, therefore, 4R, which is L vaporization, is going to be equal to, according to whatever I wrote earlier, T triple point times S4 minus, or S3 minus S4. Let me remind you, on this PT picture, I have the triple point right here. I have solid here, liquid here, and vapor here. I'm calling this point 1, 2, then 3, 4, and going back to 1, 5. I can also connect the dot here. So, S3 minus S4 times TTP is 4R, and similarly, L sublimation is equal to TP S2 minus S1, and this is 6R. Notice that TTP is the same, and I'm going to have this is 5, L fusion is equal to T Tp S4 minus S5. Now 5 and 1 are the same point, so I'm going to just club them together, or S5 equals S1. If that's the case, if I go around the circle from 1 to 5, delta S 1 to 2 to 3 to 4 to 5 is equal to 0, because S of 5 and S of 1 are the same. So I can write delta S 1 to 2 is, the L related to L sublimation, plus delta S 2 to 3 is 0, because I'm in vapor, plus delta S 3 to 4 is minus of L vaporization, plus delta S 4 to 5 is minus L fusion. So I can write this delta S1 to 2 as L sublimation divided by T triple point, which is 200. S3 to 4 is positive, so S4 to 3 is positive. I should have written this, let me correct this. This was 3 minus 4. S3 to 4 is negative, so this is going to be minus 4R over Tp. S4 to 5 is the latent heat of fusion, so this is going to be with a negative sign divided by Tp is equal to 0. L sublimation I already know is 6R. Ttp all cancels, and this gives you L fusion equals 2R. Gives you L fusion equals 2R, and that's your answer. Finally, I'm going to solve a problem on conversion of graphite to diamond. This is also taken from Finn's book, but it's a standard problem given in many, many other books. It says two common phases of carbon are diamond and graphite. At 1 atmosphere and 298 K, graphite is more stable because its Gibbs energy is lower than diamond by 2.9 kilojoules per mole. Use density of diamond equals 3520 kilogram per meter cubed, and density of graphite as 2260 kilogram per meter cubed and find the pressure required to convert graphite into diamond at 298 K. So let me remind you that what we are doing is applying this pressure at constant temperature and finding out how much pressure is required before the Gibbs energy of diamond and Gibbs energy of graphite becomes equal. So the question goes into at what pressure G graphite equals G diamond, given the data. So what is the data given? Data given is that if I plot G versus the pressure, and we have done this in the previous lectures, here is graphite and it continues like this, and here is diamond. It continues like this. And right now we are at 1 atmosphere, and graphite G is lower than the diamond G by 2.9 kilojoules per mole. And what I want to do is increase this pressure all the way up to this point, delta P, so that this gap becomes 0. Let me show this pictorially, only focusing on this region on the next slide. So what we are doing is, here is my G versus P picture, and if I just focus on that part and make it big, here is graphite, here is diamond at 1 atmosphere. This gap out here is given to be 2.9 kilojoules per mole. And as you increase the pressure by delta P, all the way up to this point where G become equal, the Gibbs free energy of diamond has gone up by this much, delta G diamond, and Gibbs free energy of graphite has gone up by this much, G graphite, and we want to know what delta P is. So let's write this as delta. So delta G graphite is going to be V specific times delta P, V specific of graphite, which is 1 over density of graphite times delta P. Similarly, delta G diamond is delta P over density of diamond. And if you look at this picture right here, this gives you that delta G graphite minus delta G diamond is equal to 2.9 kilojoules per mole. So I can convert the whole thing into per kilogram and then do my calculations. So 2.9 kilojoules per mole for diamond is going to be 2.9 divided by 12 times 10 raised to minus 3 kilojoules per kg. So I have putting in all the numbers. Density of graphite is given to be 2260. So delta P divided by 2260 minus delta P divided by the density of diamond 3520 is going to be equal to 2.9 divided by 12 times 10 raised to minus 3 kg. And this, I'm not going to solve this, gives delta P. Calculate it and find out. So with this, let me conclude this lecture. By stating that some problems related to first and second order phase transition have been solved. Thank you.